Welcome to a new video. In this video we will continue with another example about the Schmitt Trigger circuit. This will be about an asymmetric circuit where we have the lower and the higher threshold voltage not symmetric. We will see how we can determine the component values for an inverting Schmitt trigger. So we will see a design, and of course we will see how we can plot these graphs in the SPICE simulator. Of course we will first do the calculation step by step and also verify these in the SPICE simulations. Okay, let's jump right away into our objective. We will like to use this Schmitt trigger circuit, which has an output limits plus or minus 10 volts. So that's given. And we'd like to design for a lower threshold voltage of 3.4 volts and a higher threshold of 4 volts. So you see those two values are now very close to each other, both also in this case positive. Now if you compare this circuit with our discussion about the inverting Schmitt trigger, then you see that there is no R3 here, so it is actually almost the same circuit, only this R3 here added here. And that will change the situation, so we can then create or have more flexibility in order to get the values as we want here for our threshold voltage. Okay, let's first designate output limits here in more detail. We have a Vmax, which is plus 10 volts, and V minimum minus 10 volts. That's the information from here. Okay, let's first draw a diagram which relates the input voltage to the output voltage here. That is really helpful to go to our design. We have here our input, which is then changing, which is then shown here, and that output will be also two-stage, which is bistable, so we'll get plus or minus 10 volts as its value. Since it's an inverting Schmitt trigger, it should then go down at the higher threshold, which is actually shown here, so VTH. And it should then go up, so it should do the inverse at the lower threshold, so from the low state to the high state. And these two states are the Vmax and the V minimum as shown here. Now this is, as said before, very important and very helpful to start with drawing and make a sketch and then start with your analysis. Okay, let's first look at our calculations in the first step, and before we do that we designate here the V plus and the V minus nodes, and our notion here is that the two input nodes here, or two input terminals of the operational amplifier, will determine what the value of that output voltage will be. If the V plus, which is this node, is larger than the V minus, so if the non-inverting voltage is larger than the inverting voltage, then we have VO as V max, so it will be then plus 10 volts. But if it is reversed, so if this voltage is lower than the V minus, then you get a V minimum. So it is actually two states, which is also called bistable, as discussed in the previous videos. So we have now here the condition to get to the values here. Now let's now designate also this node X, which is of course effectively this one, but I would like to use that X in my next steps. Now we will now set up an equation which is called the Kirchhoff's current law here at this node X, and I will now designate the current directions to set up this equation. For the resistor R1 I will go down, which is the I1 here, and for the resistor R2 I go here to the right side, and for the resistor R3 I go up. This is just a random choice. So I can now say at this node X, I can say these three currents must add up to 0. That is the Kirchhoff's current law in the general form. Now we need to use Ohm's law to write these currents in volts over the resistors. Now what you see here, this voltage here Vx over the resistor R1 is effectively also I1. That's actually here replaced from here to there. This I2 here is actually Vx minus VO over the R2. That is shown here, that's the second part. And the final one is the I3, which is the Vx effectively minus the VCC, and that is an over R3. And that is then equal to 0, all of them. Okay, now what do we get now? Now we can say in this first condition that if the circuit is in the low state, so if the circuit is in the low stable state, which is then VO is V minimum, so that means in this condition, and we want to switch the high stable state, so we would like to go up, then we require that the Vx must be 3.4 volts. That's actually the reason why it is helpful to draw this diagram to see why and when the switching happens and what kind of requirements you have. Because this is also an inverting Schmitt trigger. So we have already some information here. Now, in order to go in the reverse direction, we can also say if the circuit is in the high state, and that means VO is Vmax, and we want to switch to the low stable state, then we require that VTH or Vx here, that node voltage must be then 4 volts. Again, because it is an inverting Schmitt trigger. Now we will see that shortly why, also in the simulator. The VCC and VEE, but these are the two supply voltages for our operation amplifier, which is a little bit larger than this 10 volts we require the output. Normally, in ideal case, you'll say, okay, this is 10, this is minus 10, then you get also 10 and a minus 10 in the output, which is not true, of course, in the reality, also not in the simulator if you use the model of an operational amplifier. So this operational amplifier will consume some power and also some energy, and of course here the voltages will go down. So I have selected here 1.5 volts up and 1.5 volt down to compensate for the losses in my operational amplifier. Now, if I now summarize these two conditions here as a statement, I can say for Vx is 3.4 volts and I have a VO which is minus 10 volts, which is actually shown here, which is minus 10 volts. We have this equation, which is actually using this equation. I can now substitute here the values I have. Now Vx is 3.4, R1, R2, R3 is still unknown. Of course, that is what we need to know. We have here again Vx 3.4 and then minus 10, because it is the VO here in this case minus 10 volts. And I have here the VCC, which is here 11.5 and again 3.4 for Vx. Now this is now an equation where you see here 3 unknowns, and we can of course use it later. Now we can now simplify this, because this 3.5 minus 10 will be then 13.4. I mean 3.4 minus 10, that will be this. And this one, 3.4 minus 11.5, will be then effectively minus 8.1. Now taking this together, we will use shortly what we need to do in order to get the values for these three resistors. Now let's call this equation number 1. In a similar case, we will do that from this condition, this statement. Use now in summary that Vx must be 4 and the VO will be then 10 volts there. Again, use the same formula here and go down here and then substitute the Vx and the VO values in the VCCs. And again, now simplify this, then you get here this equation. Now we call this equation number 2. What you see is here that we have 3 unknowns, as said, R1, R2, and R3, but only 2 equations. Now mathematically we cannot solve this, so there are many options, or actually infinite options. So we need to select one of the 3 resistors here. So I will set here now, let's say the resistor R1 to 1 kilo ohm. Really arbitrary, you can also select the R3 and R2. That doesn't matter, it will do the job also. Then I have now, from this equation, it will be then this. So I just substitute here 1000. And I also do that here 1000. So that's the only change I make. Now I have 2 equations, 2 unknowns. So I can now proceed and I can now solve this. Of course, I can also work out this one, this part. So it will be 3.4 over 1000 will be this. And I can also do that here, the same thing. Okay, perfect. Now I have now 2 equations. Let's bring them here and then move on with this one. We need to solve now the R2 and R3, and we have now R1, which is selected. We can also write these 2 equations in a similar form, in a different form, I mean, which is helpful for our solution, because we get here some fractions, which is quite annoying. And I want to have 1 over R2 written as R2 to the power minus 1, so R2 inverse, which is the same for R3 inverse and also for this equation, exact same manner. Then I make the following settings or following substitution. I call X, which is then R2 inverse, and I call Y is R3 inverse. So I call this X and this Y similarly also in this equation. Now what happens? Now you get these equations, which is in terms of X and Y pretty easy to follow instead of these annoying fractions. That's why I did it. Now I can now create a system of equations. So using 2 equations here, so I can now make that and collect them together. What I will do also here is bring these constant to the right side and also this constant to the right side. So that's actually what I did here. You see that the 0.0034 will be here minus then, and this will be also to the right side will be here minus. Now what do we see? Now we have actually here two equations to a known problem. In order to solve this, we can now make these two coefficients equal to each other, or these two coefficients equal to each other. So we need to eliminate one of these, x or y, in order to proceed and then calculate the y or the x, and then substitute that to calculate the other parameter. What we can do, or what I should do here, that's my choice, I say I will multiply the first equation by 6 and the second equation by 13.4. Why? Then I have here the same coefficient, of course, with the inverse sign, and I can then add them up. So that means the result will be 6 times the whole thing here. So this 6 times, this is 6 times, this is 6 times. You get here a result, so you can do the math for yourself. And I do now here 13.4 times each here the parts, and you get now this. And I will now add them up, because when I add them up I will lose my x, because it will be then 80.4x plus minus the same thing. So I will get rid of this x exactly as we wanted, and I have only the y, which is now adding here together, will be here minus 149.1. y is equal to, addition of these two will be still negative. Then the y will be minus 0.074 over this minus 149.1, which is a very small value. Now it is helpful to write it down in some digits, not as 4.9 or 5, let's say. So I have here 4.963 approximately times 10 to the power minus 4, which is pretty small. But this is, by the way, also a conductance, because you do here 1 over, that means actually here for the x or y, it is actually the conductance. So the units here are in Siemens. But we know that we need a resistor R3 and R2. So we can say R3 is 1 over this y, or 1 over this value, which is approximately 2 kilo ohms, or more precise 2.015 kilo ohm. So we have also R3. Then what do we do next? Now we can now substitute what we have found here, y, in one of the equations here. Let's say this one or that one. I will use this actually. So I go here and I say I replace here this to the right side, and then flip the equation, actually what you see here. Now I divide everything by 6, and then I substitute the y I have just found, and now can calculate this, and the result will be then 4.876 times 10 to the power minus 5. In a similar case, because the R2 was here given as the inverse of 1 over x, actually effectively, so I can also use that here. Substitute that here, you get now here 20.5 kilo ohm approximately, or 20.51 kilo ohms. So we have now all three resistors. By selecting R1, we have calculated R2 and R3. Okay, let's bring them here. These are the results, these are our output limits, and these are the voltages we use in our operation amplifier. Now the simulation results. This is the circuit we will use in the simulator. You see here the R1 selected, R2 20.51 kilo ohms, and R3 here 2.015 kilo ohm. This is connected to the VCC. That was also the case here for the R3. VE here is, as shown here, 11.5, and VCC is 11.5 also. So this is also exactly as we have wanted, because there are some losses in op-amp, so we go a little bit higher than the 10 volts here. And we have here selected the operation amplifier TL081. Now what do we have now? Okay, let's see the plot. This is our simulation plot. The blue one is our output and the red one is our input. The input is in this case chosen as a triangular wave with an 8 volts peak with a frequency of 100 Hz. So I would like to have just a waveform which is sufficient to go in this limit. You can of course do also 5 volts peak or even 4.5 volts peak, doesn't matter, because you get sufficient voltage. So this is just a random choice. And now you see here the output maximum, which is 9.98 volts, and output minimum, which is here minus 9.95 volts, which is this minimum value of this blue line. And we have here now in total these in the summary, which is a little bit smaller than what we wanted, but it's really good for most practical purposes. So you can say this is good enough. Let's also look at the threshold voltages here in the red ones. You see here when this voltage waveform here is getting larger and larger, and then at some point, which is now in this case a little bit larger than 4 volts, so 4.02 volts, this high state of the output will be then going down, which is inversion, so it is the inverting action. And then the VTL, which is then the lower threshold, which is at this point 3.37 volts, then I go actually from the low state again back to the high state. So in summary, I have a lower voltage or lower threshold voltage of 3.37, but my higher threshold voltage is 4.02 volts, which is a little bit smaller here and a little bit larger there. So how much I am off, in this case 20 millivolts, and here 30 millivolts. Now that is, I think, doable. So we can say we can live with that, and this is also perfectly fine. So I can say the design is complete for this circuit. Alright, this was our example considering the Schmitt trigger having asymmetric threshold voltages. So there are no, let's say, 4 and a -4 volts as the threshold voltages. We have seen how we can formulate the equations and then determine the required component values for this circuit. And then we have verified finally our result using the SPICE simulations. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.